Welcome. In this session, we will explore the critical role of network topology in AI infrastructure. We will define what topology means in this context and explain why specific designs, like rail optimization, are essential for scaling AI workloads efficiently. Start by defining network topology. Simply put, it is the roadmap of your data center how switches, cables, and servers connect. In traditional environments, we optimized for north-south traffic like a user accessing a web page. However, AI is fundamentally different. Training workloads generate massive east-west traffic where GPUs exchange gradients constantly. If your topology isn't built for this, it acts like a traffic jam, starving your expensive GPUs of data. Understanding this shift from hierarchical to high-bandwidth adjacent designs is the first step in building a scalable AI factory. This diagram compares the two traffic patterns. On the left, we see the traditional flow. Traffic moves vertically from users down to databases. It is hierarchical and predictable. On the right, we see the AI traffic flow. Notice the intense horizontal lines connecting the GPU nodes through the switch fabric. This east-west communication dominates the bandwidth, requiring a topology that prioritizes peer-to-peer speed over vertical hierarchy. Does topology matter for scalability? In AI, scalability means that if you double your GPUs, you should roughly double your training speed. However, bad topology kills this. AI jobs are tightly coupled. If one packet is delayed due to a bad path, the entire cluster waits. This is the tail latency problem. A standard topology often has blocking ratios where bandwidth is shared, causing collisions. For AI, we need non-blocking designs. Without this, more GPUs effectively slows you down because you are simply adding more opportunities for network congestion. Here we visualize the straggler problem caused by poor topology. We have 3 GPUs working in parallel. GPU 1 and 2 finish their tasks and send data quickly, entering a wait state. However, GPU 3 hits network congestion, a bottleneck shown in red. The entire cluster sync step cannot happen until GPU 3 clears that congestion. A scalable topology eliminates that red block, keeping the compute cycles aligned. To solve the congestion issue, we use a design called rail-optimized topology, the standard for NVIDIA DGX super PODs. Instead of connecting all NICs on a server to one switch, we connect them to separate parallel networks or rails. For instance, the first GPU in every server connects exclusively to the Rail 1 switch network, the second to Rail 2, and so on. This creates parallel highways for data. GPUs perform collective operations. They talk to their peers on the same rail, often avoiding the spine switches entirely, which drastically reduces latency and contention. This diagram illustrates the rail-optimized concept. Look at node A and node B. Instead of random connections, we have distinct paths. GPU 1 on node A connects via its NIC directly to the switch Rail 1, as does GPU 1 on node B. They share a dedicated network lane. Similarly, the GPU 2s connect to switch Rail 2. This physical separation prevents traffic from GPU 1 interfering with GPU 2, maximizing throughput. Finally, we connect these rails using a fat tree or Clos architecture. A fat tree is a non-blocking topology where bandwidth capacity is maintained. As you move up the layers, there is no oversubscription. Every leaf switch connects to every spine switch. This provides full bisection bandwidth, meaning any node can talk to any other node at full speed. When combined with NVIDIA NCP-AIN libraries, this topology allows the network to adapt, cutting around failures and ensuring that massive AI jobs running across thousands of GPUs maintain consistent high performance. This view shows a fat tree topology. At the bottom are our leaf switches, which aggregate the server rails. Above them are the spine switches. Notice the mesh of thick connections. Every leaf connects to every spine. This redundancy ensures that if one path is busy or fails, traffic has multiple alternative high-speed routes to reach its destination, guaranteeing the non-blocking performance AI requires.